In the name of God, hi, my name is Mohammad Mahdi Mohsenzadeh. In this project, I designed, simulated, and implemented a multi-port converter for my master thesis. In my master thesis, I proposed a family of multi-port converter with 500 kHz switching frequency. This is the first version of the converter that I designed and implemented because of these switches. First of all, I have to speak about this converter, but I cannot show its topology because I'm working on its paper, so I cannot reveal the circuit. As you can see, this converter contains two stages, and each stage is based on boost converter. And in each stage, I have a main switch, an active clamp switch. Here, main switch and active clamp switch, and this inductors are my main inductors, and this inductor are my resonant inductors, and this capacitor are my clamp capacitors. I have to mention that I used these four switches with plastic package because I decided to realize that this converter can work properly at low power or not. And after that, for high power, I changed them and I used TO 247 package for that. Now, I'm going to show the bottom of this converter. You can see the gate driver circuit is here. Each gate driver circuit, you can see I have 4 gate driver circuits. Each gate driver circuit contains a PNP resistor and diode, PNP transistor, diode, resistor, capacitor, and gate driver. This gate driver is SI8261, which is an optocoupler gate driver that I used it for high switching frequency. And I have a circuit here. It's a power supply circuit for these gate driver circuits. Each regulator provides 12 volts and 50 volts for my gate drivers, and this 12 volts is going to be connected to these min-max because I have two float switches, so I need to use isolated power supply for that. Now I'm going to show its simulation. This is the closed loop simulation of my converter because the reason that I mentioned before, I cannot show it and I use this subsystem. I have two input voltage here and one output which is connected to this, and I used these elements here to control the converter. This is my PI controller and this is the PWM unit. I use this unit again because I want to complementary signal with dead time, so this dead time generator can create that dead time for me. And I have a constant here and a triangle waveform because I'm using an interleaved structure, so I need to use two triangle waveforms, and this waveform and this waveform should have 180-degree phase shift because the interleaved it's about 360 on the number of interleaved stages. So I used a two-stage, so I need to use 180-degree phase shift between my two stages now. And I have the voltage reference is about 400 volts, and it's going to this PI controller, and I have the limiter, and that's it. For testing this converter, I changed its input voltage by this step from 70 to 80 at this time, and I changed the output load because I want to change the output power. So at this time, I changed the time. I changed the load of this converter. Now I'm going to start the simulation. As you can see, that PI controller properly works, and you can see the output voltage is stabilized on 400 volts. And at this time the output load is changed. Now the converter can stabilize 400 volts on its output port, and this time the input voltage is changed, so again the converter is able to stabilize 400 volts on its output port. Now I mentioned that this converter is based on boost converter, and we know that a boost converter has RHP 0, right half plane 0, so this converter should have that. But I designed that PI controller which removed that RHP 0 from this converter, so I don't have this problem in my converter. Now I have to say that I designed its PCB. As you can see, it's a multi-port converter, inverter, and VMC cell I used in this converter, soft switched, and the input voltage is 60 to 80 volts for the test, but this converter can work with 48 volts because I recorded a video about that, and can convert this input voltage to 400 volts, and the power of this converter is designed for 100 and to 100 and 1400 watts, but in the simulation I used that and I designed it for 104 watts, but in the practical test we didn't check that 1400 watts, only for 1000 watts, 1 kilowatts. If I want to show that, this is the input port, output port, and you can see resonant inductors, main inductors, my switches, and this is the first version, and I give signals with this. Now I'm going to show a video here. This video is about the first version of converter. I said that I decided to realize that this converter can work with this structure or not, and I didn't change the MOSFETs, the plastic package MOSFETs in this converter, but for the second version I changed them. Now okay, we are going to work on that. Now you can see this converter, one input port, second input port, output port is connected to this load, and we have this power supply for 2 input ports, and this power supply for gate driver circuits. This power supply is connected to regulator circuit, and this is the blue pill. You can see the blue pill is my microcontroller, and this blue pill, this microcontroller creates 4 signals, 2 signals for each stage with dead time. It means that for each stage it creates 2 complementary signals with dead time. Now as you can see, I gave 48.2 volts to those input ports, and the current of these input ports is about 2.3 amps, and if you time them, you can understand that this power supply is giving 100 watts to the converter. So now this is the output voltage of this converter, which is about 400 volts, and this is the first stage main switch, and this is the first stage second stage main switch. The first stage main switch is the gate source voltage, and for the second stage is the drain source voltage of main switch. As you can see, as I mentioned before, these main switches should have a 180-degree phase shift. As you can see, this one, when this switch is off, this switch is on. The first switch in the first stage, the main switch is in first stage, and the main switch is in second stage. When it's off, the switch in the second stage is on. When the switch is first stage is on, the main switch in second stage is off. Because of that, I decided to show the drain source voltage, one drain source voltage, and one gate source voltage. You can see the drain source voltage is clean. This is the experimental setup. Wait a minute. I use this differential probe because I have two different switches here, and okay, and now I'm going to calculate its efficiency. The efficiency is about 90% for this converter at 100 watts. Okay, now I have another result. I cannot show all my results, but I can show one of them. This result is for 330 watts. The output power of this converter that I tested is about 300 watts. You can see the main waveforms of one of my diode, the voltage across diode. It's very clean, and its current and the switching loss. And its unit in this oscilloscope, you can see it's about 500 nanosecond, and in one switching cycle you can see 1, 2, 3, 4 of them. It means it's about 2 microsecond, and 2 microsecond means the switching frequency is 500 kilohertz, and we don't have any switching loss here. And that's it. I hope you enjoyed it.